Good morning, class. Today we will continue discussion about the inverse Z transform. As I mentioned the last time, at the end of this class, I'm going to give you a very short quiz. Well, I call it quiz. Actually, it's a very short exercise. The important part is how you understand the material of this class, and you do the problem according to your understanding, according to your correct understanding. Then I will grade it as much as a attendance check. So let's get started. Last time we talking about the inverse Z transform. Well, we want to do that is because now we are able to find out the system function, which is right here, which is a capital H Z. It comes from YZ over XZ. It's coming from this division. Y is the output observation, X is the input observation. And very easily, we can find the system response. And that should give us the identity of my system. Now what's left is how to make this back to the impulse response. So we need to use an inverse Z transform. Inverse Z transform itself is a contour integration because Z is a complex continuous variable. And we have to do an integration, and it's contour integration. It's in the complex variable space. It's quite involved. So we are thinking about some other ways to deal with this problem. And then we end up using the power series expansion using long division and do the partial fraction expansion to find the result. Partial fraction expansion is we are doing a divide and conquer. We make this ratio of xz, which is in the format of a rational function, bz over ac. After long division, you got a proper part, you got an improper part. And then we can work on this division to smaller pieces and then make sure that all the smaller pieces has a very small order on the denominator. So for example, I have a subtract, let's say 2c to the power -1, 2. This is on the denominator, that's first order. Sometimes we may have, let's say 1 plus z to the power -1, subtract 3z to the power -2, and constant on here, 1. And we call that the second order on the denominator. All these are smaller pieces. If I can generate something on the denominator, it's smaller order, there is a way for me to look up the table and to find what's the time domain signal or the time domain system representation. And then we finish the problem, we finish the entire thing. We talk about the rational function, how to do a long division first, make sure we divide the proper part and improper part. So this, if it's rational function is improper, so we divide it into, this is the proper part. And then after long division, we can have this polynomial. You just divide by this polynomial. And then you have the proper rational function where the order of numerator is strictly smaller than the order of the denominator. And then we leave this to focus on that. But last time we were talking about the polynomial. If it's a polynomial like this, and then the inverse Z transform is very simple. It's a linear operation. Z is transformed a linear operation. Therefore, you can work on each individual term here. And then we know for this constant, it will give me a delta function, just delta n. Inverse Z transform back to time domain. In the Z domain, that's everything. So in the time domain, you have very limited. It's a delta function, delta n. If you work on this term, C1, we have a delta n minus 1. Well, z to the power -k, it's just a delay term. So no surprise, it's very simple. And this one is c sub n minus n, delta n minus m minus n, like this. Okay, so we just have a delay term. And the thing back to the time domain, it's very simple. It's just this delayed version in time domain. It's a delta delayed version. If you do convolution, it just simply you have delayed x n minus 1, x n minus 2. So we got this part done. This part we solved it. Now we are focusing on this proper rational function, b1 over a. Okay. So for that, we did some, first we changed that as a function of c to the power 1 instead of c to the power -1. So since we have a proper rational function, we can always do that, xc over z, and we can write into this as function as a polynomial of z. This is a polynomial of z, and it's also proper, meaning that the order on the numerator is strictly smaller than the order of denominator. It's proper. And then to divide it into smaller pieces according to their poles. If I have distinct poles, we are looking at the poles because we are looking at the denominator, right? Denominator is a polynomial. That polynomial equal to 0, we find the roots of that polynomial is the same that we're finding the poles of this entire thing. So if I have distinct poles, p1, p2, all the way to pn, because on the denominator, it's a polynomial of order n, so I have n poles. If they are all different, so I can divide it into this format. Divide it into smaller terms. Each term looks like this. It's a1, which is a constant. It's order 0. Divide by c, subtract p, a pole. On the denominator, it's order 1. Numerator is order 0, because original is coming from a proper rational function. When you divide it, you still divide it into proper rational function. So the order of numerator is strictly smaller than the order of denominator. Therefore, the numerator has to be a constant. We want to find those constant coefficients, a1, a2, an. If you can do that, and then I can solve for it. I just put it into smaller pieces. To do that, what we need to find is we multiply by a factor c subtract one of the poles, c sub k. If you do that, you will leave this on all the other terms except this middle term, that z subtract p sub k is canceled out. So it single out this coefficient a sub k, and then we can calculate that. If you evaluate this function, now this function is the original function we multiply by this factor. Evaluate this function at a particular point on this pole p sub k. So z equal to p sub k. And then all these terms canceled out. It's 0 here, 0 here, and we leave only this coefficient a sub k. Therefore, we can find a sub k here. And in addition, if you have another pole which is complex conjugate, you don't have to calculate. It just the coefficient will be its complex conjugate of the previous one. All right. So today we look at some other cases. If I have multiple order poles, if I have a double pole, or I have a double pole, or I have mth multiplicity of poles, so xz has a pole of multiplicity of m, so p1, p2, p3, all the way to p sub m, they are all the same. It contains the denominator, the factor of this. Then the partial fraction expansion must contain the terms. We got this term, the first one, which is z on the denominator, z subtract p sub k. The second term on the denominator is z subtract p sub k of square. And so on and so forth. We have those m different terms. And in this case, because I do the fraction expansion, so on the numerator, those are all coefficients. Those are all the coefficients. Zeros are the coefficients. That has nothing to do with z. If you have a z here, you can also do this expansion. You just make it one of those terms. So we divide this into that many terms. Only the denominator has the value of has the variable z. On the numerator, those are all the coefficients. It's just a number, it's a coefficient. And then we want to find those coefficients. For the poles of multiplicity of m, I need to find all these m coefficients. If we multiply a factor, let's look at it. If we multiply factor z subtract p sub k to the power am, evaluate on the pole z equals to p sub k, and we know all these, we leave something here, but this term, you will cancel out this part, only a sub mk left. So we can immediately find out the coefficient here, a sub mk. Now about the other coefficients, what we do is we take this guy, and differentiate it with respect to z. So d, this guy over dz. Now evaluate on the same z equal to p sub k, evaluate on the pole. If you do that, what we have here is I have actually, you take the derivative, you put a z subtract p sub k here, m minus 1, right? And you take some constant over, it's okay. And then you work with my original function, which is here. This is my original function, which is here. And then you will find out you only leave a term am minus 1 of k, which is, this is singled out, a coefficient. All the other term will cancel out. Therefore, if I evaluate at z equal to p sub k, and then give me this coefficient, it's singled out coefficient, a sub m minus 1 k. Similarly, I can continue to do this differential with respect to z. Here is the m minus 1 differentiation, and then all those terms, everything will cancel out. It single out the coefficient on the first term. If we evaluate on that, all the other terms, because we will have a z subtract pk, this term in it, you multiply by that, evaluate on this, cancel out, and single out only the a1k, which is here, a1k. So this is a method that it looks a little tedious to do that because you need to do differentiation, but it's very nicely defined. It's easy to program, easy to calculate. And in most of the case, we don't need to go that further, because for a real coefficiented sequence or signal, probably you only have a pole of order 1, a pole of a multiplicity of 2, and it will stop there. So it's calculable, it's doable. Now we look at this final result. Suppose we have used my partial fraction expansion. Okay, we find this, and then we calculate all these coefficients. These are already calculated using the previous 2 pages, how we do that. And then what we can do is we multiply this function by z. The reason is we want to recover my original signal, which is hz. And also, when you multiply by z, it will be very straightforward to convert that into 1 subtract p1 times z to the power negative 1, right? Because when you do this z subtract p1, we multiply by z equals to is 1 subtract p1 is 1 over, which is z to the power negative 1. Similarly, we have these. Now this looks very nice because z transform, usually we like to represent that as a function of z to the power negative 1. And why we do that? Well, physical meaning is that z to the power negative 1 is a one-time unit delay. So whatever you have that's xn minus 1. Delay is easy to understand because you can store this value. Now, if it's z to the power positive 1, that is a time advance. You're trying to get some signal in the future, which we don't have that yet, right? Theoretically, we don't have that yet. So it's not causal. So we like to have something in delay. And of course, everything is put into this format in our z transform pair table. Everything is in z to the power negative 1. So it's easy for us to get back to those data. Okay, now once we find each one of those as this, that, and that, to do an inverse Z transform, because inverse Z transform is a linear operation, again, that's a linear operation, so I can work on each individual terms. If we work on the first term, A1 is a constant, so you can bring that out of the inverse Z transform. What's left is we are working on inverse Z transform 1 over 1 subtract P sub k C to the power -1. And this is very easy to do, the inverse Z transform. We already know that. And if you want to check back the table, you will find out this is simply a P sub k times to the power n if it's causal. Causal, I'm putting a step function here. If it's anti-causal, then I put a kind of this anti-step function. That's u n, -1. We also have this P sub k, the pole to the power n, but remember we put a negative sign here. Okay, now let's just look at this part, causal signal. If it's causal, this translates to P k to the power n. That's it, right? It's very simple. If it's causal, well, this unit function just to emphasize is a causal. So when n is less than 0, everything is 0. What is this in time domain? This guy. We have seen that before, is when we're dealing with a root, when we're dealing with roots of a polynomial, we're solving for a difference equation. And it gives us the form, any roots, right? Lambda k, if these are the roots of the characteristic polynomial, then the solution for this difference equation is that the roots to the power n. That's exactly what we have here, right? Those roots are just poles on my Z transform. So once you find a pole, then the time domain is this pole to the power n. They have a 1-to-1 correspondence. It's easy to understand, easy to remember. Okay. In case of a double pole, so in case I have a pole which is multiplicity of 2, so do the same thing, you multiply it by Z, and we have translate everything as a function of Z to the power -1, Z to the power -1. And it's also very easy to find the time domain signal. When we look up the table, we find out if it's causal, what I have here, the time domain is n times P to the power n. On the other hand, if it's anti-causal, you have n to the power P to the power n, but put a negative sign here. Now this is also very nice because the second term here, because this term here looks like that, right? So you have a pole, but you also putting n here. That is what we have in solving the difference equation. If you have a multiplicity of the roots, I also have a second term of this. Now you remember that I have a first term, which is P to the power n. Where does that come from? Well, that comes from when I solve for the other multiplicity, and I don't have a Z -1 here, and then we got this first term. If you have something here, the second term is this, you multiply by n. So it matches very well what we understand before for the difference equation. So indeed, we can always, in Z transform, for looking up table, we find out that. And then the format is very familiar. We can recognize that. So usually what we need to do is we need to deal with a multiplicity of 2, because for any real signal, if little xn is real signal, or if you transfer that onto a Z domain, the coefficient A's and the B's are real. If they are real, I know I can always decompose into this format. So the first one is a polynomial by doing a long division. And then you have these terms are all the single poles. The single poles with all the alpha and the betas, they are all real coefficients. You have that. I have K1 terms here. I also have another sum here with K2 terms, where I can write out in this format, and then the denominator is order of 2. Now, in this case, everything here, the coefficients alphas and the betas, all these coefficients are real. Okay, then I have that. So in this case, of course, K1 plus 2K2, because everything here with each term of that, I have 2 poles. So K1 plus 2K2 equals to n. That's the order of my system. That's the order of my denominator, and that's the number of the poles. And all these coefficients are real. You can put into some sum term, you can put into a product of these. And in this sum term, and we can, using the lookup table, to find the time domain equivalent of these signals, using the lookup table to find the time domain equivalent of these signals when the denominator is only of order 2. Therefore, theoretically, for all the real signals, we can simply using the lookup table to find each of those time domain signals, time domain representations. So we kind of complete the loop. We're doing something, moving everything to the Z domain, find the system function capital H, then we're doing an inverse Z transform back to the time domain to identify the system, find the little hn. So let's look at some extensions, more general analysis of linear time systems in the Z domain. In general, it is a zero-pole system. Zero-pole system meaning that I have HZ. This is my system. Zero-pole meaning that I have a polynomial B, A, both have some orders greater than 0, greater than equal to 1. So you have both zeros and a poles of the system. Represented by linear constant coefficient difference equation with arbitrary initial conditions. So if I have a zero-pole system represented by that, let's look at, well, we know this represents a difference equation, it represents a system. So let's look at the system with some inputs. So right now here is my H. See, I have my input, I have my output. Well, input is xn, output is yn. I bring everything to the Z domain. So the input is xz, output is yz. Assume that the input signal xn has a rational Z transform as well. So xz can also be represented by this fractional format, n z over qz. Each of n and q are polynomials of z, or polynomials of z to the power -1. The system is initially relaxed, therefore y -1, y -2, all the way to y -n equal to 0. Then the output simply a product. Right? It's a product of system times input. So we put in the system is my fractional equation b over a. The input is fractional equation n over q, so I can put into this term. And then the yz, I can also discuss the zeros of yz, the poles of yz. So for example, the poles of yz will be the poles of h containing here, plus the poles of input signal xz contained here in q. Suppose that the system contains simple poles p1, p2, all the way to pn, n poles. And the Z transform of the input signal contains poles q1, q2 to ql, where all these poles are distinct. In addition, suppose that there is no zero-pole cancellation. So we leave all these coefficients, the polynomials intact. There's no cancellation. Doing a partial fraction expansion on yc, that will yield something like that. Because I know the poles, I know what are the poles, p's and q's. So it can be extended into this expansion. We have all the sum with all these distinct poles of p's. So we got a sum like that. And then we have a sum on the second part with the distinct poles on q sub case, well, L poles. do the inverse Z transform on Y. So Yn is here. And then for all these inverse Z transform on each term, that's very simple. That is of denominator order 1. Therefore, the Z transform is simply the root. We take the pole of P, the root to the power n. That's it, right? So very easy to do this inverse Z transform. The poles are the roots to the power n. And then A sub k, these are the coefficients. So you pull this out of this, so A sub k. And make sure we are talking about causal signal. So UN, putting a UN here. And so sum them together. Similarly, when we do for the second term of the input signal, we have all these poles of Q sub k. So we have time domain, that's the roots Q sub k to the power n, and times the constant coefficient Q sub k. Emphasize everything is causal, so we put a U of n, that's a step function here. So the first term, we call that the natural response of the system. The second term, we call the forced response. Natural response, given that it is a natural involvement of my system, has nothing to do with input signal X. It will happen anyways, because this is according to your system H. The second term is forced response. It is forced by the input signal X. So everything follow the input signal. So let me write out this again. So the first part is the natural response. So that is the sum of all these. So if P sub k, all these poles are less than 1 for all k. So all these poles are within the unit circle, or all these roots has an absolute value less than 1. Then if you look into this term here, it's to the power n, this term will decay to 0 as n approaches infinity, right? So when this n takes 0, 1, 2, it becomes a very large number, and this term will become 0. This one will tend to be 0. So this entire thing, the natural response will decay to 0, if this is true. And the natural response, indeed, in this case, we call that a transient response. So an example is that you have a circuit board originally excited by a signal of frequency 100 hertz, and then you change to another signal by 200 hertz. So eventually, whatever you have on the circuit board will follow that 200 hertz, but there is a period called transient response, transient time. It's not going to jump immediately. You'll have this time. The system will evolve or adapt itself to the final input. So the transient will eventually, the effect will die out. It will follow the input. The transient phenomenon will die out. So this is the decay. That's the natural response. The second term is the forced response, is this term. So if the poles force on the unit circle, now why we do that? Well, it's your signal. The signal itself is not going to be diverged. You're not going to provide me with a signal that's become larger and larger and larger and larger without any limit. It's just physically impossible, right? So the worst thing you can have is a signal that it never ends. It's a sine wave. And most likely that's the case. You provide with some oscillation. This oscillation is always there. You have a sine wave, a cosine wave. So the poles are formed on the unit circle. Well, we will see that later on, because on the unit circle, the unit circle is exactly z equal to j to the power z equal to e to the power j omega, where omega is the frequency. So if I'm not having any signals diverge or disappearing, it's a sine wave, and the signal is on the unit circle. So we like to have all these, if I have a pulse on the unit circle, meaning that I have a signal oscillating all the time. Consequently, the forced response persists for all n greater than 0. So it will follow the input. It never dies. It's just a sine wave, always oscillating. But the forced response is called a steady state response of the system. Eventually, it will follow the characteristic of the input, which is determined by the roots which is determined by the pulse, which is Q here, Q sub K. Okay, so we got those two parts, natural response and forced response of a system. Okay, so let's look at some characteristic of some special system. For causal system, if I have a causal linear time invariant system, in time domain, this is its definition. If we're looking at the system impulse response, Hn, when n is less than 0, the impulse response is 0. So if you draw this on a picture, this is time n, 0, 1, 2, 3, -1, -2. So causal system is that you got some h here, but you're not going to have h here. That's all zeros. So you only have the negative, when the negative time you have h values. So that's a causal linear time invariant. The region of convergence of the Z transform of a causal sequence is the exterior of circle. So we know that for a causal system, the region of convergence is the shaded region like that. It's always an exterior of a circle. So a linear time invariant system is causal if and only if the region of convergence of the system function is the exterior of a circle with a finite radius. So this is radius of R. We have to have a finite radius. If R is mathematically, you can have some extreme example. R is infinity, and then I don't have any. But we have to, here we have to define that this R is finite. I will always have the region of convergence. Region of convergence is exterior of this circle, and also including a point at infinity. Mathematically speaking, that's also, on the complex plane, that's also another point at infinity. We're including that point. If I have a system that's stable, it's BIBO stable, bounded input, bounded output stable. We know that we need to have this absolute summable, this property here on the impulse response Hn. So looking to the Z domain, Hz is equal to this, right? This is simply the definition equation. We are doing the Z transform on Hz. So Hz is less than or equal to, we're putting this absolute value should be here, here. Less than or equal to, we're putting the absolute value inside the sum. And then this is equal. You can put it in this absolute value on each term. Less than or equal to that. Then we evaluate the Hz on the unit circle. That is, we are taking the absolute value of Z equal to 1. When we do that, if we evaluate at this, now the second term becomes 1. So you can simply remove that in your equation. And then we have Hz less than or equal to this. Because it's BIBO stable, it's absolutely summable. Therefore, this is less than infinity. Conclusion is that the region of convergence includes the unit circle. Right? This is convergence. It's less than, you have Hz, absolute value less than infinity. It converges. It converges. It is evaluated on the unit circle. Therefore, the region of convergence includes the unit circle. I need to point out here, now, evaluate the Z transform on the unit circle has a special meaning. It's very important because, as I said, we can always write this. Where here omega is the radiance of frequency, that's J 2 e to the 2 pi of f. F is the frequency. So later on we will know we are only focused on this particular region. That's my frequency. That's a special case of Z transform where Z is a polar term. It says amplitude times e to the power j omega. When this guy becomes 1, when rho is 1, or Z absolute value is 1, we only look at on the Z, on the unit circle. And that's, we only care about the frequency. It has a special meaning because later on, everything for a real system, we are checking with the frequency. You are always evaluated on the unit circle. Therefore, in general, whether it's causal or non-causal. In general, if my unit of circle, if I check in on that, the unit of circle should be always convergent if I have a stable system, right? If you check on the unit of the unit circle, that you're checking on all these frequencies. If the system is good, if the system is stable, that means you should have everything is converged. In other words, that if I have a good system, meaning that I have a stable system, you look at the unit of circle, the unit circle should always be in the region of convergence. Okay, so the previous two ideas, we're putting them together. If I have a causal system and a stable system, a causal and a stable linear time invariant system must have a system function converges for C greater than R, because that's causal, exteriors of circle, where R is less than 1. R is less than 1. So this R, this is region of convergence. R should be less than 1 because unit circle should be here. That's the radius of 1. We said the region of convergence should including the unit circle, right? So it should be there. So a causal LTI system is BIBO stable if and only if all the poles of HZ are inside the unit circle. Well, if this is true, now if I have a pole here, this pole P1 has to be here, right? Because inside this, that's the region of divergence, if you like. I just created this word. It diverges because the shaded region, everything here, here, these are the region of convergence. By its definition, those are the HZ that is finite. And what's the definition of a pole? Now, if you got a pole here, a P here, P, that is HP. When you add a pole, this guy becomes infinitely large. Oh, that's fine. Therefore, the pole cannot be in the region of convergence. So logically, in this case, it has to be within the circle of R, and R is strictly smaller than 1. Therefore, the pole should be within the unit circle. Okay. Compare this with what we have learned before in signal system. That is a causal linear time invariant system with a rational transfer function HS, the Laplace domain, right? HS is stable if and only if all poles of HS are in the left half of the S-plane. That is, the real part of all poles are negative. So we are looking, this is the S-plane, the real part, imaginary part. If it's stable, that means all the poles are in the left half. The poles will be here. Left half of the S-plane, if this is a stable system, okay? So this is, we compare with the Laplace transform with continuous signal. You can picture that as if I'm taking the imaginary axis and bend it, somehow bend it, and make it a circle. So it will kind of make it a circle, and then including all these poles, that the poles should be within the unit circle. And then that is equivalent. We are talking about the stability. So anyways, just something that we kind of recall what we had before. Also, the position of poles in the S-plane will determine the stability of the system. Okay, so now the last, as I said, let's do some work together. And I'll call this a quiz. So I will ask you to work on that for 10 minutes, the rest of the class, and then send me your answers through chat or send me an email about your answer. Okay, so the question is like this. Let me explain this a little bit. So I have a linear time invariant system characterized by the system function HZ. And I already do this partial fraction expansion for you. So we got those. And you will find, using these, you can find out the poles of the system. I want you to specify the region of convergence of HZ first part. You have two parts to do for each problem, don't forget. The first one is to specify the region of convergence. The second one is you need to find out the impulse response of these three different conditions. The first one is the system is stable. The system is stable. The second is I tell you the system is causal. The third is I tell you that the system is anti-causal. So for different conditions, you specify the region of convergence and find Hn. This is also the hint that the same system function, I may have different Hn according to whether it's causal or anti-causal, so on and so forth. Okay, so let's work on that.